Okay, hi everyone. Welcome to our fifth session of the MedAI exchange. This week we have Joseph Cohen with us to talk about his research on counterfactual generation of text X-rays using autoencoders. Joseph is a postdoc at Stanford, affiliated with the Amy Center. His research interests include tackling challenges related to deploying AI tools in medicine, especially computer vision and genomics. He's also the director of the Institute for Reproducible Research, a US nonprofit which operates shortscience.org and academic torrents. So as always, we hope that we can try to make this session as interactive as possible. So the audience, please feel free to unmute yourself to ask questions or type in the chat. And Joseph, before we start, do you have any preference about when you would like to take in questions?
Whenever is fine.
Okay. Yeah. Without further ado, let's welcome Joseph to give his talk.
Oh, great. Thanks for having me. So yeah, this work is going to be presented soon at Middle. This is kind of a preview of the presentation. First, I want to start off with the motivations. It's going to be a few slides on this, and I want to get some interaction with the group. So I'm going to ask you how confident you are in a neural network model's prediction, and then if you just put in the chat like 1 or 5, just like write them all so we can get like some idea of what people think. And then the model that we're going to be using was designed for frontal chest X-ray images. Okay, so this model for this image predicts that for this image, there's a 80% probability of an enlarged heart. So how confident are you in that model's prediction? Okay, there's a 2. Okay, 5. Okay, man. Okay, well, okay. So what about this picture? 4. So it's gone down for someone. Okay. But it's higher. Okay, so this was trained on frontal chest X-rays. Okay. So what about this one? So now they're all predicting 80% probability. So now for this one, let's see what the score is. So the first one was maybe an average of 2. The second one maybe an average of 3. Now people are giving 1s and 5s. Okay, maybe the average is more 4. Okay. So it's higher. So this is the source code of that model. So we were interpreting those predictions with way more confidence than we should have, right? So I want to talk about the issues when we're deploying these models. And there's going to be 2 main ones. So I'm going to go over the first one, which is out of distribution samples. So let's say we have a model that has been trained on data and specifically been trained on frontal chest X-rays. All right, so a lot of things can be considered out of distribution. So pictures of cats are obviously out of distribution. We shouldn't expect any prediction to be reasonable. Where this gets tricky is in these other 2 use cases, as were defined by this paper, Chow et al., where we have incorrectly acquired images. So a lateral view doesn't fit the protocol for a frontal chest X-ray, so that's out of distribution. The image could be overexposed or incorrectly cropped. The normalization of that image could be wrong, and all these things are going to throw off a network. Use case 3 is another more subtle one, where the images are right, except there's some selection bias that has caused these the content of that image to differ from the training data. So if we only trained our model on patients between 18 and 30, none of them are probably going to have pacemakers or a very small amount. So that when it gets deployed, if it's applied to patients 70 and up, there's going to be a lot more pacemakers, and is that going to mess up the prediction? And so it may, and so we need to be concerned about when we apply these models to data that it's operating on data that we have an expected level of performance, right? And these out of distribution cases are gonna mess that up. Another issue, besides just, let's say we have a correct model applied to out of distribution, is you can have a model that's learned some incorrect attribution for some task you'd like to predict. So for some, if it's trying to predict an enlarged heart, maybe there's some bias in the data where the shoulder indicates, correlates really well with that enlarged heart label. So the model doesn't actually have to look at the heart to make its prediction. It can just look at some artifact. So this can often happen when you merge two hospitals together. You get a lot of site-specific artifacts between them, and then the model will actually look at the wrong thing. Oh, question? So what we want, besides this out of distribution issue, we also have models that are just not right for the right reasons, or maybe on some subset of demographics, it looks at some spurious feature, but for other parts of the demographic of the training data, it looks at the right feature. So it's really hard to make sure that these models are helping and are being right for the right reasons and not making mistakes. So a common approach to look at this is this saliency map or attribution map, which is often, if you break it down, it's just a first order approximation of the neural network, right? In this really simple partial derivative where you have the change in the output label or some task you want to predict, that probability, with respect to all your input pixels, right? And you get these maps that are shown above, and there's a bunch of different flavors of how to do this. And there are a lot of issues with them. So they help us to detect some things, but it's we can do better. The first issue is that some of these methods, they value appearance over accuracy. So there'll be an experiment that we talk about later that you can see this, but they'll largely look at edges and show edges as the features, because that makes us think that it's explaining the prediction better, even though it's just looking at high contrast edges in the input image that aren't related to the prediction at all. Another issue is that these attributions can be completely arbitrary and unrelated to the prediction. So you can train a model that doesn't generate attribution maps that are reasonable at all, even though the model is predicting using the correct features, right? So a lot to be concerned about here. Also, these spurious attributions are often just ignored when a Gaussian blur is applied to make them look better. So a lot of these things get doctored so that we value the appearance of them over what they're actually telling us, right? And that these artifacts that where it's attributing some importance to in the corner, that's like a mistake of the model. Why is the model looking in the corner? So we should be concerned about models when they're doing that. Okay, so how to address this false positive, false negative problem? Because this is the bottleneck preventing these models from being deployed into practice. That's my opinion. I believe that's true. So the viewpoint that I take, that we kind of move forward in this work, is moving towards this AI in doctor symbiosis, right? And the way we're going to do that is by generating counterfactual images as animations, where we can generate a version of the patient that does not have that pathology and make it very clear what that means, and try to really convey that feature that's being looked at in a very graphical way as a GIF. And if you think about why this is better, right? So if models can convey their predictions graphically, like as we see here, and then physicians can use their knowledge to make sure that's reasonable, and to have that really higher level intelligence to interpret the prediction of that model, right? And these can go hand in hand, and we'll be able to hopefully avoid these false positives that are due to some artifact in the fact that where the model is looking at the wrong thing, or that it's because it's an out of distribution sample, it's looking at all sorts of wrong things, to really make sure it's a reasonable prediction. Great. So to convey this point, I want to put you through a simulated reader study, which is similar to what we've done later for this work, but it will kind of help to motivate everything now. Now we're going to look at a model that's predicted that this image, and this is a real model, that's predicted that this image has an enlarged heart with 61%, right? Do you think it's right? Right, so we don't need to get the feedback. But here is a regular image gradient, right? That lets you see this first order approximation of why the prediction is being made. And you can kind of, often I feel like an issue here is because there's highlighting in some places, a physician could just believe.
Sorry, Joseph, I just have one quick question about your input, about your image gradient. What is the value for the filtering for your image gradient? It doesn't seem that you are visualizing all the gradients, so you should have a threshold, right?
Oh, yes. Okay, yeah. So this is like the 95 or 90%. Okay. Yeah, sorry. The 90 or 95% highest impact gradient features. Yeah, because
and you are analyzing each of the gradients individually. You are not analyzing it based on some kind of spatial correlation between the input gradients. So for example, imagine that you have a lot of like noise as input gradients, like very few pixels here and there, which is highlighted in the input gradient, but you are not doing any kind of like post-processing after you get the input gradients, right? You just visualize it based on threshold.
Yeah, well, yeah. So they're ranked. So it's like so we get a percentile, and then that's all we're showing you. So there's no blurring or anything after the fact. Yeah. Yeah, with the blurring, I think it actually subtracts from what it's actually conveying, and I think it often lets us paint a picture that's not there, right? Because this is the raw gradients are what the model is actually outputting, right? So we should just have a method that outputs these smoother if we want them smoother.
Okay, makes sense. Yeah, makes sense. Yeah.
Okay, so this is what I'll call like the traditional attribution map approaches with this image gradient. I didn't put the other ones here because they all kind of look like this one. And then I'm going to show you the latent shift approach to doing this. So here we have a 2D version of the latent shift approach as well as a 3D version of this. So I'll talk about why we can have both for the same interpretation. But given this view, does that make you more or less confident in the prediction of this model that they have an enlarged type? And the ground truth label is that this person does have an enlarged type. So that's an easy case. So what about this one? So the model predicts that this patient has an enlarged type with a higher probability, 65%. Is it right? How confident are you in this? And so we see with the traditional silencing map, it's kind of all over the place. You could argue it is looking at the heart, right? And I feel like that's a fallacy that we look at these sentence maps and say, well, it's kind of looking in the right area, even though it's looking at all this other stuff. We apply this latent shift approach. The 2D version is not great, but we can see that the animation really shows that it's focusing on something else that's not the heart. And then
sorry, I have another question. So in the 3D version, it's not really clear like what you want to focus. So your bright color is focusing the model attention, or what you want to focus on the 3D version?
Oh, the 3D version, you mean the GIF?
Yep, yeah.
Okay. Oh, so I'll go over how this works in the next slides, but I guess I'm presenting it out of context just to
right, exactly, because your latent shift part is clear, right? Because you are showing the coloring and you're showing the highlighted location, but the 3D version is not clear really, like what it is showing.
Yeah, well, so this 2D image is actually computed from the
3D
GIF.
image, right? Okay.
Yeah. So this is just like a projection of the maximum difference of this image. So here we're like removing the enlarged heart from the image, right? And it's not even focusing on the heart here.
I have a question here. So the input image that you're showing here looks like to be underexposed. Is that like an intended example for this like input, or I guess my question is that can we do some pre-processing on these images before feeding them to the model, like I guess a very simple probably histogram equalization, improve the visualization at least so we can see the heart and ribs and stuff. Is that something that we want to do, or we just want to model be able to deal with all raw images without any pre-processing?
So for the first question of this is that there's like an issue with the acquisition. There may be if it's underexposed. I just tried to find an image that predicted a high value but was actually negative. So I mined from a data set an out of distribution sample. So there's something wrong with this. You have more insight than I do. I just know that the model is wrong when it makes this prediction, because the ground truth is actually false for this. But yeah, so I think, I mean, here
so when you're saying the ground truth is false, I mean, is the radiologist making the evaluation based on the exact input image, or they do some processing on that? Because it's really hard even for radiologists, I guess, to work on this image, you know, without any further assistance. I mean, how confident someone is going to, you know, evaluate this?
Yeah, so that's a good point that we haven't analyzed here is that baseline confidence. So here it's like the NIH data set, so we just have binary labels. We don't have any confidence associated with it.
Okay.
And I think that, you know, they're forced to make a decision, or this is actually mined from the clinical data. So it's mined from the radiology report. So maybe they had access to other images or other information to make that distinction.
So, Mahmood, I can probably answer that a little bit. So this data set actually has the all frontal as well as the lateral view. So you can imagine, you can imagine the radiologists have access to two different views of the same patient. Okay, so but they have actually extra information to make. Yeah, another image of the same patient. So for example, lateral view probably is better. The heart, especially like in large heart, that's the prediction. Probably it's better visualized in the lateral view than in the frontal view. I see. Yeah, I mean, my whole point, I guess, was, you know, when we are saying that the ground truth is false, but the model making the the true decision, I mean, how confident we are that, you know, the ground truth was actually false or not. So yeah, I guess we can move on. Thank you.
Yeah. So, and I think there's another good point of do we want the model to be to take any kind of input? Oh, sorry. Do we want to have the model take any sort of input? And I think that's not the goal of this work, but I think that would be nice. But I think we should at least know that the model, if we see this output here, where it's kind of not making as much sense, we could adjust the image to make sure that it is in the right, it's in the domain of the model, right?
Yeah, that's, I guess, what I meant. Yeah.
Yeah. Also, I think that the way to interpret this example is just because it's a false positive here, it could be a true positive, but it's made for the wrong reason. So maybe that's a better way of illustrating this point. So this person could have an enlarged heart, and this label is wrong, but still, like, the model is not looking at the heart to make its prediction, and that's why we should be concerned with trusting that the radiologist should trust their own instincts instead of the model, because the model is not offering any assistance here.
Yeah, now it makes sense.
Yeah, that's what I meant. So maybe this, I'm casting this as a false positive problem on this slide, but we almost don't even need to see the label, because we just shouldn't trust any prediction, even if the patient has an enlarged heart or not. This is just the model that is not adding any information here. Great. Okay, so to build these type of GIF animation models, there's been a bunch of work, namely the papers that are here in the corner, and there's two reasons why they're hard to get working. The first one is GANs, although great for making really realistic images and learning really great latent spaces, they're really hard to train. And so getting some model that does the job is you know, GAN is kind of maybe an overkill for that. Although I think it's a good way of making these models. Also, some of these existing methods have a really monolithic design, right? So that the classifier and the method that generates these images, it's all one big monolithically trained model, which is for one, really difficult to implement and train, and two, doesn't give us this modular design. So what we'd like to do is take any classifier that exists that, you know, takes in pixels and be able to generate these explanations for that existing model, right? Yeah, and also not have to rely on GANs. So these are the two kind of design principles. And then the idea for this work that I'm going to talk about is to make the simplest possible method to make this work, just so it's easy to implement. Because I tried to implement these baseline methods and they were too complicated for me. So that's the motivation. So the core approach is training an autoencoder, which is the basic autoencoder. We have an encoder and a decoder, takes in an image, reconstructs an image. And you can see it trained here. If you ignore the other stuff, it takes in this image, encodes it as some latent code, and then reconstructs it into a reconstructed input image. That's blurry because it's using a squared loss. So unfortunately, that's kind of an artifact most of the time with these models. It doesn't necessarily have to be. It just seems to be the way they come out. And then there's a fixed bottleneck, which is important here. It's not a UNet. There's no transverse connections that can go across to make the image crisper, which would be nice, but then we wouldn't have this latent space to move in, right? And so with this, we also take any off-the-shelf classifier that can take in the reconstructed images. And so the way this approach is going to work is we're going to take an input image, encode it down to this latent space, decode it back to this to the image space, and then take this reconstructed image and put that in the classifier, right? And from there, we can compute this gradient, right? So here, this is going to be this reconstructed image, this encoded latent value, right? Decoded back to the image, put into the classifier, and then we're looking at the output prediction here for a mass. We're looking at a mass, right? And then we're going to say, well, how could we move this latent value, this latent vector, such that we increase or decrease the prediction of mass on that classifier, right? And that's just going to define a vector in this latent space. And then we can apply this gradient by some lambda to go in the positive direction, where we'll make the mass worse, right? Or we can subtract that lambda, right, to then decrease the prediction to make the mass go away. And that's the entire idea.
Can I ask a
Yeah, go ahead, Nadira, sorry.
No, I just wanted to clarify how did you actually ensure that the feature that you're interested in, which in this example is the mass, how do you get that access in your latent space?
Exactly. I want to ask the same thing. So are you using the prediction by the fast classifier, or are you using the ground truth levels for this mass?
Oh, I'm using the prediction of the classifier. Yeah, so we don't need any, we just need the classifier weights. That's the whole thing. So
imagine that if you put the image at the beginning, like imagine that you put the image in your decoder give you the fast image set, right? Like fast decoded image set, fast decoded image, sorry. And then you put it in the classifier, and the classifier predicted mass as the highest prediction. So you just take that, right? Without verifying it with the ground truth.
Yeah. So we can compute this even if it's not positive for mass. Any image that gets reconstructed. Yeah. So we don't have to care about the labels here.
Okay. So you are doing this class, like the classifier actually is pre-trained on some other data set, right?
Yep. Yeah.
Okay.
Yeah. So I'll show later. We're gonna have 3 different classifiers that we're looking at how they vary on the same data set, on the same autoencoder. We can see how they actually move the latent space in different ways.
Okay, and that, sorry.
Yeah, just I wanted to make sure I understood this. So the classifier is pre-trained to identify the presence of masses in any given image. So it's actually a segmentation task that it's pre-trained.
No, it's not a segment. This is a
binary classifier.
Yeah, you can also do it with segmentation. That would also work. It'd be a cool project because it's not, we don't demonstrate it here, but segmentation is just a bunch of classifications. So you could make that work. But here it's just predicting like a probability between 0 and 1.
I see. And so assuming that the classifier is like it's trained well enough that it can identify the presence of mass, and that's why it's classifying. So you kind of make that assumption that the classifier is good enough to make representations that are predictive of its task. Is that correct?
Yeah, definitely. The classifier needs to be able to predict. Yeah, well, I mean, it's almost like a chicken and an egg, because the classifier needs to be good enough to predict using the correct features, or I mean, you can explain the prediction of any classifier. So it doesn't, the classifier doesn't have to be good. This is, I mean, this is a way you can take a classifier that's that has something wrong with it, right? And then look at what it's predicting using, and then figure out like if there's something wrong with that prediction, and then train the classifier again to fix it. But yeah, so the idea is you have some classifier that's been trained, and now however it is making a prediction, we can understand why.
I see. Okay.
Because it may be looking at the mass here, but it's also looking at something else, right? And then we'll see that with this with this explanation, because it'll show like all the features that it's looking at. So here this happens to be like really good at detecting masses, and specifically this mass, right? Because this is a big mass. There's issues with nodules. I mean, the classifier is not that good at other things. But it's good at this mass, and so it only varies that mass in this image.
Got it. Okay.
Why do you need to go through a latent space?
Okay, yeah. So I forgot to add all the type of intuition on this. So typically, if you just looked at the image, right, you're just generating a traditional adversarial attack, right? Where it might even be one pixel, and then that pixel will that'll be like a really bright pixel. You get these like weird, I should have had those images on here. You get these weird like transformations that are just like a tiny set of movements everywhere, and then it's imperceptible. The image looks exactly the same, right? And then yet it'll make a change in the classifier's prediction. And so this is not what we want. So we want the exact opposite of an adversarial attack. We want it to change the image such that it changes the class for us, right? Or however it's predicting. But the autoencoder acts as an approximation of the data manifold. So we want to move on the data manifold, and if we're just walking on the image space, we're not near the data manifold, because like you just perturb some pixels and it's not a realistic image anymore. So this model will work. Like the better the latent method you have, the more that movement is constrained, right? So in this lambda transformation, in this lambda shift, latent shift, the way we wanted to transform it, it has to, the only degrees of freedom it has are in that learned latent space. So it has to change features in the input image, but it's constrained by what the decoder allows it to, by how the decoder allows it to move. And the decoder has learned that like this is a mass and there's like some size attribute, that makes it bigger or smaller, or there's like one that's on the heart and it'll make the heart bigger or smaller. Like these attributes that are learned while it's learning to compress the representation of the image. So it's constrained in its movements, and that makes the image changes more realistic because it can't do these adversarial attacks.
But it shouldn't be also depends on the dimension of your latent space.
Yeah, I have a whole slide about that. Yeah, this is a big problem. Yeah. So yeah, there's like a sweet spot. It's a hyperparameter, sadly, with this model.
Just one clarification, maybe. Here, the data that F is trained on and the autoencoder is trained on are different data sets, right? They're not the same, or they can be, but they don't have to be. They're not all. But the way this autoencoder is trained is for a subset of it. There's a few classifiers that we're evaluating where there's no overlap between this. But for one of the classifiers, it overlaps a few data sets in there. Yeah, so they don't have to be the same. I think it's better if they're not, because then you can completely avoid this issue of like data leakage between them. Yeah, so the beauty of this is you can train an autoencoder or grab one from the library that we released with this, right? And then you can take a classifier from anywhere. Although I found out it's very hard to get the weights of trained classifiers for chest X-ray online, but you can, if you find them, you can just, it doesn't matter what data they're trained on. You can use it here, as long as the autoencoder generates images that are within like the same domain as that classifier, right? So I guess, I mean, you have to do some scaling to make sure that they're like everything's normalized in the same manner. But yeah, you can plug and play these things and it'll work. Cool.
Okay, so more, I mean, I kind of want to jump ahead to training the autoencoder, but this is I'll explain how we generate these 2D images and the GIFs. At this 0 point here, what this means is that if we don't do any lambda shift, this is the prediction of the classifier, right? So it's like, I don't know, 0.75, right? And then as we move in the negative direction, which we found is better for making these images, if we move in the negative direction, we subtract 10 times that gradient, right, from the z vector, right, and then reconstruct it, and then make a prediction on the classifier. We get something that's lower here, right? So the prediction will go down, right? Empirically, we find that like minus 30% of the prediction looks the best, right? If you go too far, you get these crazy changes that you have a completely distorted image. And if you go too little, you get almost no change in the image, right? So it's really, we found that generally 30% works. But there's also a caveat here is the models that we're using are calibrated such that 0.5, a 50% prediction, is the operating point of the AUC curve, right? So it's the point of maximum uncertainty of that model. And so I think this normalization definitely helps scale what that transformation does. Because if you just take a random classifier, its kind of active range is going to be, between 0 and like 0.0001, and right in between there is a really good, could be performing really well, but it's not really interpretable as a probability. So here these things are normalized and calibrated, so that's 30% means more. Okay, so what we can do so we established the negative lambda where we move negative 30%, and then we'll just chop up this interval into some number, right? As meant, these are the frames of your GIF, right? So it can be like 10 images or 5 images. And then you get this transformation. So you can see this here, that there's no mass here where we subtracted it. And then at 0, we can see that there is a mass where we didn't do any transformation. You can see that changes. And then if we look at the maximum difference between all these images, we can construct a 2D version of this. And that's this resulting image here. So it gives you a really nice looking heat map. And if you did a lower threshold, so this is like 90 or 95% percentile of the pixels. If you went even lower, you'd get like a perfect circle right around the mass. So that would be really cool.
But I have just another quick question. So did you compare the finally generated 2D image with the occlusion map?
With the occlusion map?
Yeah.
Like using an occlusion method? No, we compared it with other saliency.
Because I think if you compare, it's like not theoretically probably they are similar, but like in practice, if you compute the occlusion map and what method you are using for generating the 2D pixel, it should be pretty similar. If the classifier
for mass, I would say
yeah.
But for
the mass, I'm not talking about like other abnormality, but for mass, fracture, this kind of like definitive abnormality in locations, I think occlusion map should perform very similar to this one.
Yeah. So I guess the reason I usually don't include occlusion maps in these works is you have to tune the size of your patch, and then the computational cost is like super crazy for generating all these on a classifier, on one of these chest X-ray classifiers. So so usually and I think it can work better, but it requires those hyperparameter tunings. But for stuff like an enlarged heart, that wouldn't work the same. Because where's your patch going to go? And if you make a really big patch and you block up the entire heart, yeah. So I think for mass it might be a good way, but if you can have multiple masses too, and so this method will also take into account the multiple masses, and you'll see multiple things grow and shrink. Where with an occlusion map, with occlusion, you wouldn't see any difference because it would still predict mass with high probability, and you'll only be covering up one of them.
So when you generate these GIFs, do you go negative lambda for positive predictions and positive lambda for negative predictions? Or?
So we don't. I haven't applied it to positive predictions because it's more about just like here you're just hallucinating what's a healthy person would look like with some pathology. But yeah, going negative for a positive prediction looks the best, because it's just removing that prediction and making that X-ray, that chest X-ray, look normal, or not, doesn't have to be normal. It's just without that single pathology. So the person could have two pathologies and you're just subtracting one from it.
I see. So the main use case is more for detecting like false positives, or to assist with the positives, not with the negatives in that case, right?
Yeah, well, I think also negatives, it's when geared towards false positives, right? But with false negatives, it could be, yeah, I guess you would, yeah, it wouldn't work for that, right? So if it's negative, it's already low, but you could try to make the prediction even lower. So we didn't explore making it higher.
Okay.
But yeah, so I guess, yeah, false positives is the main point.
Sounds good. Thank you.
I wrote positive and negative at the beginning, but it's just false positive. It's the only thing we're doing here.
Cool.
Cool. So here's some more analysis on these like shift plots. And the main takeaway here is that we run these 4 different tasks, is that it's more monotonically decreasing in the negative direction, right? Where in the positive direction, when you start increasing this, it goes up a little bit and then it goes down, right? And it's not as consistent. And what this actually looks like is like really distorted looking images, because it's still able to generate, these are images that are adversarial images. I mean, they're going to be fooling this classifier, but they can make make arbitrary looking things that will fool the classifier. So it's still an issue with this. But generally, it looks it's pretty consistent. And then the slope of these plots is highly dependent on the autoencoder, where if you change the autoencoder, the slope is going to be a lot different, so it might be a lot sharper. And I didn't add, so here there's 3 independently trained classifiers. This is one found on GitHub. It's like from JF Healthcare in the Checkspert challenge. And so I didn't train it at all. These other 2 are trained as part of this Torch X-ray vision library. So this one is just trained on the MIMIC data set from MIT, and the JF Healthcare one is just trained on the Checkspert data from Stanford. And then this all model is trained on like 7 different large data sets. And you can see that they're predicting at different points, but they're all kind of reacting differently. And here the autoencoder is the same across all the tasks and all the models, right? So there's some interesting dynamics there. Okay, so one question with this model, and the autoencoder is still, it's a few slides away, is that how do we tell whether this model better captures IOUs, better captures the pathologies, right? And so one approach is to compute an IOU between the some high percentile of the attribution map and some expert labeled bounding boxes, right? So here we have one for cardiomegaly from the NIH data set. And then we can look at the IOU between these saliency maps and the bounding boxes. We find that they're really all the same. And I have a big table to show you on the next slide, but they're generally all similar, right? And they vary. There's not really one winner. I mean, they vary a little bit, but I wouldn't say that it's like knocking it out of the park. But intuitively, they look much better. They're really highlighting attributes that look like part of the enlarged heart or the mass, right? Where these other methods are, they have these speckles, and then so it brings a lot of doubt. So maybe IOU analysis is not the best evaluation for this, right? So which motivates later a reader study that we do to see if it can improve performance. But here's like a big table of IOU analysis where we look at 6 different tasks. Here's like a preview of the masks. We evaluate and compare it to like image gradient, guided backprop, integrated gradients, or this latent shift approach that we're using. And then here's 3 different models. We have the AUC performance, which is all pretty high across the board. It's high-ish, right? They're very good at cardiomegaly, and the IOUs are generally consistent. There's not one that's going to be better. The one main thing to take away from this is that pneumothorax has a high AUC but very low, very low IOU, right? And then we'll see later that the radiologists who were involved said that this model, like its predictions about pneumothorax, don't make any sense. So likely we have some sort of incorrect feature attribution or some other issue where it's not actually predicting pneumothorax or using those features. Great. Okay, so when training this autoencoder, there's a bunch of different configurations that we can have. So the main one is a bottleneck, right? And then we can have so it's a ResNet autoencoder, and the depth can also be varied there, right? And so here is like a way of looking at all these trainings. So here is this image, and you can see the reconstructed image in the background here, as well as the latent shift max, the maximum difference between all the frames that we get. You can see its image here, the heat map, the attribution map overlaid there. And I guess what takeaways that I've noticed is when you have a very high dimension, right? The images look much better, like the resolution is really nice and sharp. But then when it does its transformations, it kind of just seems to like appear, some new image will just kind of appear in these little spots, kind of appear. It changes in these little areas. So it's really weird. Although it is transforming the image, it doesn't really look satisfactory, right? And if we go too low, so here is the bottleneck is 2,000 dimensions, and these images are 224 by 224. So it's going from 224 by 224 to this 2,000 dimensional vector. We get very blurry reconstructed images. But if we look at the animations here, they look really good. It's clearly moving the heart. But for fine features like a mass, it's not going to do that well because it's not really visible because the whole image is so blurry, right? So we really have to really tune this parameter based on the tasks that we want to do well at. So in this work we use the 4,000 dimensional one because it seemed to be good. Some other takeaways are here. We have the IOU and then the mean absolute error of the reconstructed images on some fixed test set here, and it's kind of all over the place. There seems to be when you have high MAE, so you have a high reconstruction error, you have lower IOU, and then when you have a low reconstruction error, you get higher IOU. But it's not super consistent. Here we vary
the colors represent there.
So here, so the color is the epoch, the training epoch.
Oh, I see.
Yeah, because it wasn't clear where to early stop. So there was no really great heuristic to early stop this model or tune the hyperparameter. So it's me looking at the animations and saying this one's great. So there was a lack of rigor in selecting those. But each model took 2 weeks to train, so it was really a difficult process. So this is a very not comprehensive way, and the model is chosen almost purely based on intuition, and then the metrics are computed after. So definitely a limitation in this. It's not really rigorously chosen. Yeah. So the main takeaway: you got to find a bottleneck right in the middle. Another analysis we did was the analysis and sanity checks for saliency maps, where the idea is that if you're randomizing the weights of the classifier, starting from the classifier layer and going all the way back towards the first layer of convolutions, that the saliency maps that are generated by that model should have less and less correlation with the salience maps that are generated using a classifier with all of its weights intact, right? So you could say like a model with all random weights should have its saliency map should have no correlation with the trained model's saliency map, right? That's the idea. And so that's this part over here. So this is a fully randomized model. And you can see there's still a difference, right, between some of these. And then as we go back, we'd expect less and less, we expect more and more correlation, right? But the best outcome for this is that the second you randomize the classifier, everything goes down to 0. That's not the case for any of these methods. But the latent shift method, when you randomize that classifier layer, it goes immediately down. So it's not very well correlated, where guided backprop is still pretty highly correlated, which is scary. And so this analysis is interesting, shows a this is not drastically different, but it's in a good positive direction, showing this method is conveying that information and kind of stays random for the entire way. So stays the same level of correlation, where the other ones are still decreasing, which is questionable. Okay, so the IOU analysis wasn't really good, so it's really hard to get answer the question of like, is this better with some sort of objectivity, right? So we did a reader study to see if it would help spot false positive predictions. And so we have 240 chest X-rays, and then 50 of these are false positives, and these are mined by just a script that loads an image, makes a prediction, checks against the ground truth. If it's like, if the model predicts like 70% or more, then that's a positive prediction. And if the ground truth is negative, it's considered a false positive. So we mine the data to get these false positives. And then we present these to two radiologists in this interface. So you can see it's like it's a web-based thing. And then they have method A and method B. Method A is the traditional method, so this input gradient and the basic salience map approaches. Method B is the latent shift approach only, so they don't see that version. And all they see is the 2D latent shift as well as the GIF that's animated, right? And they're asked two questions: how confident are you in the model's prediction, and is the model looking at the correct feature? And some feedback before I talk about the results are generally they say that the new prediction method is more intuitive for most of the pathologies, and then pneumothorax like doesn't make any sense, which is consistent with the IOU results we got. Latent shift does much better than gradients A, right? So B is much better than A. These are all really, I guess, celebratory. Great. Okay, so if we look at these results, what we'd like to see between the true positives and false positives is a much bigger separation between these predictions. Something that looks like pneumothorax, right? Where we have, for true positives, we're all the way over at 5, all the density is at 5. And then for false positives, all the density is at 1, right? Except unfortunately, we don't observe that. We see a slight difference. For mass, the false positives get rated at more like a neutral across the board, where the true positives are much higher. But for some things like lung opacity and effusion and electrocyst, there's hardly a difference between these scores, right? Although there is a statistically significant difference for true positives. So for true positives, there's a 0.15 increase on the scale between 1 to 5. There's an increase when using the latent shift method. So people are more confident in the prediction when it's a true positive. And that's a good low P. And for false positives, there is an increase, right? But it's very small and it's not significant, right? So we'd like this to be negative and significant, but it's not. So that's the way the cookie crumbles. So I think there's insights here on how to do a better study. And I think the key is just more education to kind of explain how that neural network latent space is working, and maybe explain the method more, because we really, just as you experienced at the beginning, I didn't tell you how the method worked before we went into these details, and that was definitely missing with this, and it's a completely new method. So I think the radiologists were not maybe seeing what the image was displaying to them. And another result from the study is how confident that that the model is looking at the correct feature. And we found this nice correlation where, so here we're just doing a regression because the data is really hard to look at all by itself. So we have these like smooth regression lines. So if the radiologist rated a 5, then it's here, and those IOUs are higher, right? So the IOU score was high when they rated a 5, and IOU score was low when they rated a low score, right? So it's not a super, good, we'd like it this, these would be 1, that would be great. So I think this is saying that there is some relationship here. High IOU scores maybe 3 is pretty good if they're rating it a 5. Right, but we'd like to have IOU at somewhere like 90. So we'd like to have some sort of proxy for having people involved. So that would be, it'd be better if we could do this in a more computational approach, so we didn't have to rely on people, or just need that physical, people power to do these evaluations, because it's just going to slow down the development. But so IOU is maybe not the best proxy, but it's not random. Okay, one plug for the framework that I've been developing and then used in this project called Torch Revision, where you can load a bunch of models and compare them side by side. And you could load, there's more than 7 data sets now. I think maybe we're up to 10. So 10 different data sets. They all have load identically. So you can just swap them out and evaluate your model, and all the images are normalized, and everything comes in as array of pixels, even if it's on the disk as a DICOM or a PNG or a JPEG. All that stuff gets normalized out. And there's a bunch of convenience utilities here to make this stuff work well. And also the autoencoder that's used is available in this library now. So you can actually recreate the images right from this library. There's a script to do it. Great, and that's it.
Thank you for the great talk, Joseph. Anyone has questions here?
I
have a.
Sorry,
Go ahead.
Go ahead,
Go ahead, please.
Yeah, so Joseph, I have one quick question about your IOU. So the IOU example that you showed us, it just seems like a bounding box.
Yeah. Oh, yes. So it depends on. So for cardiomegaly, we have square bounding boxes, and then pneumothorax, it's the only thing that looks like a segmentation.
Right. Because this is also challenging, since you are doing the evaluation for the IOU for the overall, and if you have different segmentation masks, it's not really generalizable for the comparison purpose, And so
I don't know what you mean. So I mean, these masks are all public, so you could.
I just for your reader study, when you are doing a reader study validation with IOU, I personally don't really think that having this kind of varying masks where you have a segmentation mask, bounding box, everything. Yeah, exactly for this purpose, So because it cannot be evaluated equally, because you're just varying on the latent space, but you're just changing some very minute pixel feature. And when you have a bounding box for the whole heart, for example, heart enlargement, it's impossible to correlate that. It's kind of a very challenging problem.
Yeah, there was some really good criticism, similar to I think what you're getting at from the reviewers when we submitted this paper, where they said for cardiomegaly, there's two things that could make it lower, right? You could shrink the size of the heart, or you could increase the size of the thorax, which I thought was really interesting, because the bounding boxes we had were just around the heart. In our model,
yeah, exactly. It's like cardiomegaly. You can imagine that it's a shadow of heart, right? So the thing is that you need the heart as well as the surrounding location, otherwise it's not possible. And yeah. Yep. And also for your model prediction, also for the silencer map, you can clearly see that they're looking actually slightly around the boundary of the heart, not actually on the heart.
Definitely. Yeah.
Right.
Yeah, and definitely models need to look at other things to localize themselves, right? So, which I think that could be an issue with the silencer map. But so here we're using that just to transform the image. So hopefully we get around what it's really looking at. I mean, I guess it could be looking at some pixels here to just figure out what a gray value is, so it can identify where the heart is, because the intensity of that.
I think the more more interesting comparison would be with eye tracking versus this one.
Oh yeah, I just saw that data set, so I haven't.
Yeah, exactly. I was about to suggest you the data set actually, anyways.
Yeah, that would be a great follow up, because I haven't looked at what the data looks like, but does it look like something like this?
Yes, yeah. Not really like this, yeah. Not really like this, but at least better than the bounding box.
Okay, yeah, that would be a better. Yeah, so I think they're definitely in this research that we found evaluating it was really difficult. So maybe the eye tracking makes the most sense that we compare against that. So whether IOU with the eye tracking is going to be good, but I should run it when I get some time. Thanks.
Do you think the nature of the autoencoder makes any difference in the sense of that, you could potentially, try to use one of the techniques to disentangle representations, or form ones that maintain edges using a VQ encoding or things like that?
Yeah, so as long as there's a fixed latent space, although maybe even a hierarchical latent space, like that could also be possible. So because you could have multiple Zs too, but as long as there's some latent space and it doesn't have like it doesn't ship the image towards the reconstruction to try to really make it high and accurate. I think there's a bunch of caveats with the autoencoder, right? Because it has to represent the features that you want to have the model kind of explain, right? So it could be for some of these that the autoencoder just doesn't see that feature, and then even though the classifier does make a good prediction, the autoencoder is not able to express that in its latent space, so it makes nonsense looking reconstructions. So that's definitely a possibility. So the way I've thought about this is comparing two classifiers is almost the only fair way to say that a classifier doesn't represent something well, right? So if you have, because you can swap out classifiers there. So if you have one classifier and it makes a mass appear and disappear, right? Now you know that autoencoder is capable of making the mass, of modulating that mass, right? So if you attach another classifier and then you try to have it make a prediction about a mass and then explain that prediction, and if it doesn't move the mass, you can then conclude, I think, that that classifier is not looking at that mass, right? Because the autoencoder has almost been proven to be able to represent that. So I don't know if that makes sense, but I think from the angle of the autoencoder, the representational model, the better you have, the better this explanation is going to be. But if it doesn't represent a feature, then you're not going to be able to explain that feature is being looked at or used.
Right. Yeah, and it has to be like along a single, essentially, line in the high space, right? I mean, a directional gradient.
Yeah. But it's I mean, depending on the length, the dimensionality, you can move in, for this one you can move in 4,000 dimensions simultaneously. So that gradient is moving all of those at once.
Yeah.
So I don't think it's too much of a constraint, but yeah, it has to be represented somewhere. So if you wanted to explain two things at once, then it has to kind of go in two directions, then it wouldn't be able to.
Right. To follow up, do you think, obviously there's a huge flexibility in the autoencoder method, but do you think it would be practical to try this just as a demonstration with an actual hand-built parameterization? So, like with the heart, maybe that's not the best example to start with, but you could have a 3D model of the heart and actually just make it bigger, project it down to a thing, and that could be a differentiable model, and see if that picks out these issues.
Yeah. So a fixed decoder, right? Okay. Yeah, definitely. I mean, the classifier just has to be able to make its prediction from that. But so if it's able to generate images, I mean, do you have that? I'd love to work on that. So that sounds really interesting, because you can exercise all sorts of stuff. Possibly use it to train a better model too.
Yeah.
But yeah, so I think the hard part is, the autoencoder is just a way to build that decoder, right?
Yeah.
Another issue is that here, using the autoencoder, we can get these reconstructed images that look very similar to the input image, right? Because the goal is to explain why that this input image had a prediction of cardiomegaly or mass, right? So that's why these reconstructed images are kind of keyed off that. But if you had a fixed decoder, you'd have to have some way of making this image, decoded to look like something like that. And so I think that would require an encoder from a natural, you'd have to like get that, those decoded images would have to like look like this image under question, right? And I feel like that might be really hard. So I don't know if you have a solution to that, but.
Yeah, there might be for X-rays, or it might be you have to go to a simpler problem.
Oh, so we're over time. So sorry.
One quick question. So when you were doing the reader analysis, you presented the 2D image to the readers instead of the GIF, right?
Yeah. Well, we presented both. So I mean, I can.
Oh, it presented both. Yeah, because I'm thinking that for example, for enlarged heart, because you are subtracting from the maximum, you are subtracting the maximum image with the minimum constructed image. So that's why the saliency or the latent shift saliency map is surrounded on the outside of the heart. Yeah, so I'm wondering, like, maybe it might be maybe it might be clearer if they look at the 3D, the GIF version of it, so that they can see that the heart is really like moving, and it's where the model is focused on.
Definitely, yeah. So there's another comment from reviewers that the reviewer was upset that we showed the readers both the 2D and the 3D at the same time.
Mm-hmm.
So here the comparison is between this view where they're just looking at the latent shift explanation, or the view with all the 2D static images.
Okay, I see.
So I think I think this is I think this is nicer to look at, right? But we can't tell the difference between whether the 2D version and the 3D version, which one's better, because we were showing them at the same time. So the idea is, because there was not a large, there was an increase in confidence, but it wasn't so crazy. And so independently, these methods might not, they're not going to do more independently. So I don't know if that's getting to your point, but we showed them both.
Yeah.
The 2D for me helped me localize where I should be looking in the 3D one, because here I didn't, I might not notice at first look here, but it's actually moving something about the edge of the lungs here, right?
Mm-hmm.
And you can kind of see that. So having the 2D image helps you figure out what's moving here. So I think they're very complementary with it. So.
Thanks. Any other questions?
Yeah, I have one, but if you're out of time, let me ask it.
Yeah.
So it's also related to the previous autoencoder question. So rather than using a regular autoencoder, wouldn't it be more meaningful to have a generative model there, like more specifically a variation autoencoder, because you're traversing through this latent space, and with the variation one, it's going to be more continuous.
Mm-hmm.
Whereas with the regular autoencoder you're using, you don't know if you have that continuity, and most likely you might not have. So my question is, wouldn't it be more useful to have a variation autoencoder than there, as opposed to addition?
I don't know about exactly a variational autoencoder. I think having there's tons of other methods that will generate like better representations.
Yeah.
Right?
Yeah.
An important aspect of this, and maybe this would be some issue if you had too much of a generative model, is we want to be able to encode an image and then reconstruct an image that looks very similar, right?
Mm-hmm.
And so maybe you can get a VAE that works like that, but I think the fact that you're training in a random fashion is going to give you samples that are maybe not identical, right, to the input image, right?
Yeah.
But so, having like just a discriminator on the decoder just to make it look better, I think could maybe also make the latent space look better. I think this like approaches like metric learning, deep metric learning that are going to make the latent space like much better. I think yes, they're all going to make it way better. So this is like any improvement in representation is just going to make this better. The idea with the autoencoder is just I was looking into these other methods, and they were so complicated to implement. I just wanted like, what's the simplest possible way I can get a model that does what I want it to do? Because I wanted to like just have a really simple setup, because then you have less hyperparameters, less moving parts. Which also, here it's a proof of concept that you can get away with an autoencoder to like get the job done. So hopefully, for instead of really requiring that expertise to train a more complicated representation learning model, it's much simpler to train an autoencoder. So I think more people can adopt that method because it might be good enough to get the job that they need to get done. So that was the idea. So of a proof by example that autoencoders are sufficient for some tasks here. Although I think, for larger images or getting better, smaller features, you're just going to need a better model. Autoencoders may not be able to do that, with the amount of computation we have. So maybe just adding a discriminator is going to make it look better. I think those are all bonuses, but the core like latent shift traversal would apply to any model that can condense an input image to that one latent vector.
Yeah, I agree. But yeah, still having that continuity in the latent space, as you mentioned, would be more representative of whatever you have.
Yeah, and it's here, right? So we found like this model miraculously has a nice smooth.
Yeah.
I guess it could be better. It can always be better, but it's not at higher. If you have a huge dimensionality, you get nice looking images, but then they really aren't contiguous. Like when you start moving in the latent space, it like changes dramatically to another image. Where if you tune the hyperparameters right like this, you get a smoother but blurry kind of a set of images, right? Where it'll slowly transition to another image, which is what we want here for these animations.
Yeah, thank you. It was a great talk.
Thanks.
Okay, any other questions?
I actually have more of a thought or a different application. It's kind of related to Kagan and Chris's point before as well. So moving in the latent space is actually giving you a way to generate new views of the same image. So while one like as you mentioned, it's a chicken and egg problem. So you can use, if you have better representations, you can use this method to make it more explainable. But you can also use this method to make representations better, because now you can use contrastive technique. You can start to see if I move the lambda to a certain point, then it's a negative sample, versus if I move a lambda very close, then it's probably just a positive sample and should be considered as such in a contrastive technique. And so I was thinking, what are your thoughts on like taking this work to that direction?
Yeah, I think there's a lot of potential. One issue with this method is in order to do this search, it's an iterative search, which is not great. I think there's a way to make that faster. It's just pretty slow. But yeah, if you wanted to generate those examples, I think what you're getting there is you're able. I think in a semi-supervised setting, I think would be good, because the autoencoder can be trained on tons of unlabeled data, or whatever representation model, right? It can be trained on tons of data without labels. And then when you generate, when you use that classifier, so if you have a classifier that's not that great, and it generates images that are moving through that latent space, I mean, that new image is defined by what that classifier already knows. So, what can you gain? So the fact that your transformation is constrained by the autoencoder, maybe that's going to allow you to take into account some structural information. But if the vector in that latent space was defined with kind of a nonsense classifier, then the example you get is also nonsense, right? So it might not help your classifier.
On the other hand, if you have a reasonably well-performing classifier, you can get representations that are actually more meaningful. Like for instance, there might be confounding factors in a person's X-ray. Like you can have multiple conditions, but then this method, I think, will actually allow you to get a contrasting image in only one direction, as opposed to like any direction, if that makes sense. Like for instance, you can have, let's say the person's chest X-ray has an abnormal mass as well as pneumothorax, and you can get an image that has only the mass to be removed, but the pneumothorax is still present. So that can be a more valuable contrastive image compared to just generating any other, like a completely normal contrasting image, if that makes sense.
Yeah, potentially in some, I feel like you're getting near like a zero-shot learning scenario where you're generating the samples, like you're defining what that sample should have. Yeah, I think there's something there. I don't know how to use that, right? But you could remove a mass in the pneumothorax right there. Although this doesn't work with pneumothorax, but you could remove the mass and they're still going to have an enlarged heart. So I think that approach could. I think there's something. I think there's something there to gain. Some, it's all about with those. It's almost like it's always about like how are you extracting the extra information from the unlabeled data, right? Because a lot of these scenarios where you try to do stuff, it's like where's the extra information coming from? Like if you just build a generative model and generate samples from it, then you have no more information than the original data had, right? So if you train the classifier on the same data that the autoencoder was trained on, right? Then where's the extra information, because the classifier already saw it. So if you were generating those contrastive samples with the idea that all this unlabeled data had those two pathologies and it learned that the autoencoder learned how to disentangle those, and you want to train the classifier to, right? Then that's I'd say there's something in that direction. But I think that there's some promise there with that.
Thank you.
Okay, so we are running late today. If there's no other questions, let's give Joseph a virtual applause here. Thank you, Joseph, for the amazing talk. And if anyone of you has questions later, feel free to fill your questions in the Google form. I have posted in chat, and it's also available on our MedAI website. All right, thank you, everyone, and see you next week.
Thanks.
Thank you, Joseph.
Thank you, Joseph. Bye-bye.